Okay, so this is an interesting scheduling of talks because the previous presentation was about authentication in the physical world. And this one is going to be about authentication in the virtual world. And authentication in general is a very hard topic. And one of the players that makes all of this possible is called JWT. And what powers JWT are the principles of cryptography. So a little bit about me. Hi, I'm Stefan Zhelyazkov, and I work at Musala as an associate architect. As Christo rightly said, the areas that I currently focus on are digital signing and public key cryptography. And previously, I worked for several years in the United States at companies of various sizes. So you've probably seen this everywhere. These are the two most popular and the most dreaded fields on any website. You need your username and password. And you need this for your online banking, social network, professional network, or your email account, or when you use a search engine, or for video streaming, or your phone carrier, as well as when you do like shopping, maybe for food or clothes or technology, gadgets, and the list just keeps growing. And what's more important is that each of these websites asks you to register uniquely with it, and it's preferable if you use a different password. And on top of that, the password must be something that is hard to guess. Like it needs to use uppercase characters, lowercase characters, special characters, digits, and this is difficult. And so a lot of modern browsers, what they do is they actually suggest to you strong, secure passwords, like this one. I mean, what is this? Like, how can you remember this? Like, we're all human. Like, a password is supposed to be intelligible. It's supposed to be something that you can actually remember. Like, password consists of two parts. Password, it needs to be a word, something that you can actually put your head. And if for all of these websites you need a unique password, and you put them together, it's going to look something like this. And can you remember this? Like at this point, all that we need is just put a header and a footer, and we figured out how OpenSSL generates certificates. This is a joke. It does not work that way. So it would be great if we can live in a world where we just don't use passwords. Literally, it will be great. But at the same time, because we use different apps, we actually need something to uniquely authenticate ourselves. It's got to be something different that provides each time. And so there is a solution for this, and we're going to look at that in a little bit. But you might also notice that on the slide, there is a third bullet point, and it's empty. And that's because there is another challenge that we need to solve, and we're going to look at that in a little bit. But first, let's solve the first two problems. So here we have something called a session ID. So our user Ivan is a fan of VistaCon, and he uses the app, and he supplies his credentials, and the server returns a session ID. So what does the session look like? Well, let's take a look at a server. So here I'm showing you two screenshots from a real Apache server that I have at home. And so in the bottom screenshot, I've catted the session, and I can see what's in the session. I can see my first name is there, my last name. There's also expiration date for the session, other information. And so what's interesting is that this is in the session. This information is in the session. Where does that session live? Well, let's take a look at the first screenshot. It lives on the hard drive of the server. It's literally on the physical server in a directory. And so maybe at this point you're starting to see a problem, but let's look at an example. So what if we take this server and we replicate it multiple times? This is very common for modern day apps. And in front of it, we put a load balancer. And so we still have our user Ivan. He sends a request with his credentials, and the first server returns back to him the session ID. Now, Ivan wants to go to a different page on the app. So in the subsequent HTTP request, he submits the session. But this time, the load balancer sends the request to the last server in this picture. What do you guys think the server says? It says, excuse me, but who are you? And that is exactly the problem. In this setup, the last server does not know who that person is. And so this is the third bullet point. We need to fix this for a replicated environment. And so, ladies and gentlemen, here I present to you the JWT. What is the JWT? Well, it stands for JSON Web Token. It's supposed to contain in itself the information that we need to know about the user. So pay attention to this. The session, the information lives on the server. In the JWT, it's in the token, and the token is on the client side. Different setup. Now, because of this, it has to be small because you're going to send this in every request. So if you have a lot of network traffic, it's got to fit in. Now, the JWT has two flavors, JWS and JW. They both have claims. We're going to look at that in a little bit. And something that I found interesting is that the W in JWT is pronounced like the Greek letter omega. It's pronounced jot. And I know some people call it jot, but more people call it JWT, including myself. And so what is the diagram, the relationship between the different tokens? So JWT is actually an abstract idea. And it has two implementations. One is JSON Web Signature. The other one is JSON Web Encryption. And at this point, you might be like, wait, I only know about JWT. What are these other two guys? And the truth is, JWS is what everybody calls JWT. Basically, JWE is not in the picture. So the wisdom of the day is JWT is JWS. And I'm going to use these two interchangeably. But we'll look into details in a little bit. Now, let's take a look at this structure because it's more popular. You've seen it. So it consists of three parts. It has a Josie header, which I also call Jose header. And the header contains information about the cryptographic algorithm that is used. In this case, it's HMAC with SHA-256 hashing function. The type of the token is JWT. Now, the second object is the claims. This is what I said earlier about the information. It lives in the token, not on the server, in the token. So here we have the subject. So SUB is subject, EXP is expiry. And ISS is not the International Space Station, it's issuer. And recently I had a funny anecdote at work where I wanted to add a custom property, and so I called it cus. And a colleague asked me, why didn't you just call it custom? Like, what's the big deal? And I said, well, I follow the conventions of JWT. So, and the last component is signature. That is also base64 encoded, and this is a cryptographic signature. When we look at when all of this is put together, it looks like this. The three components, you can see them colored in different colors. So we have the header, the content, the claims, and the signature. And so when we take a look again at the two different structures, JWS and JWE, they actually look like this. So in the JWS, or what we call JWT, we have the header dot claims dot signature. Now, JWE is a little more interesting. It has 5 components. It has, again, the header, which contains the cryptographic information. It has the key that encrypts the data, real encryption. It has an initialization vector, then the cipher, which contains the encrypted information, and authentication tag at the end, which is just for verification. But again, this structure is not popular. I don't want to talk much about it, just this is the slide, because it's not popular on the web and people mostly use JWSs. Now again, something that maybe comes to mind is when you look at this and it looks like gibberish, you can't read it, and you think, oh my God, this must be encrypted, I can't read it. No, it's not encrypted. Just because you can't read it, it doesn't mean it's encrypted. Actually, encoding, in this case base64 URL encoding, is different from encryption. In encoding, you convert characters from one type to another type, and you can do that back and forth. There's actually things online, websites you can go to, and you can convert back and forth between base64. So all of this means that the claims, the information in the token is public. It's always public. So this is something that is important. And here I'm showing to you how base64 URL encoding can convert between the claims back and forth. Again, this is the important information in the token. Now, you might think then, well, I don't want everybody on the internet to see what's in the token. How do I protect this? One option for you is to use JWE. Another option is to use secure protocols like HTTPS, because there, everything is encrypted, including the headers. And the token lives in the authentication header, so it's encrypted as well. So this is a solution. And also, something that is important as well is that if you don't want your token, or you worry your token might be read by someone that shouldn't, then just don't put sensitive information in it. Don't put your social security number, personal identification number, passport ID, or something like that. It's not supposed to be in that token. Like, just put information like that is enough for you to authenticate on a server. Now, authentication, as I said earlier, is difficult to get right. And how do we trust this technology? Well, the reason we trust it is because it employs the principles of cryptography. So here are the abbreviations. HS256 stands for HMAC with SHA-256. RS256 is RSA algorithm with, again, SHA-256 hash function. ES256 is elliptic curve digital signing algorithm with a curve with a hashing function. And we use these algorithms to verify the tokens. So let's look at this, at the first one, as an example. So HMAC stands for hash-based message authentication code, which uses an internal hashing function, SHA-256 in this case. So here we can see that we have Ivan again. He wants to log in onto the servers, but the servers have a special key on each of the servers. So this is something that is embedded, hard-coded in the server, and the server is replicated. This server can issue tokens using that secret, using the HMAC algorithm. So Ivan submits his credentials and gets back from the server a JWT. Now he stores it locally in the browser, and then on every subsequent request, he can send that token over to the server, and it doesn't matter which server it hits. Each of them know the secret, and they can use the secret to verify the message. So they both sign and verify the message with the same secret. So this is a very simple scenario for where you control the whole application and you decide on the authentication. A different mechanism is to use public key cryptography. So here we have RSA and ECDSA. RSA, a popular algorithm for cryptography. It uses the theory of very large semi-primes. And large semi-primes are the product of large prime numbers. So it relies on that theory. And ECDSA is elliptic curve digital signing algorithm. It uses elliptic curves, a special type of mathematical functions. And specifically, this curve in this case is P256. That's a special curve in that algorithm. I'm just reading the abbreviations for you. Now, how does this work? Well, in this case, we actually don't have just one thing, like a secret on a server. We have two things, a private key and a public key. The private key must stay secure in the server. The public key can be public. Anybody can read it. You can send it to friends. You can send it everywhere. Now, how does this token then authenticate? Well, Ivan submits his credentials. The server receives the credentials and issues a token using the private key. And then on subsequent requests, Ivan sends back that token in the request, and then the server can use the public key to verify it. And this all works good, but when you control the server, you might as well use HMAC because it's just one piece, and you can use it back and forth. The public-private key relationship is more powerful in situations like this. Let's say you have a website that you want to log into, and a lot of websites nowadays actually provide you with this option to use an identity provider. And so in this case, Stack Overflow trusts these identity providers. It trusts Google or GitHub or Facebook. And pay attention to this. It doesn't say sign up or register. It says log in, because that's what you do. You actually can log in without creating a profile. How does that work? Well, we have this identity provider G, and Ivan submits his credentials to G. G has a private key, which it keeps private, but also has a public key, and everybody can read that key. And so when we receive the token from Google, then we can send it in our requests to our application. And then the server can look up the public key, verify the token, and it lets you in. And in this case, we can even improve it a little bit. Why don't we just memorize this public key? I mean, this public key isn't going to change often. So we can just put it in the server and launch many instances of that server. And it's always going to trust that issuer. And so with this, we've actually solved the 3 problems. We can log in without passwords. Each time we log into a different service using an identity provider, we have a different JWT, which acts like a password in this case. And this all works in a replicated environment. And with this, I thank you very much for your attention.
We can have a couple of questions, actually. So who would like to try first? We have one question there.
My question is, how do you invalidate those tokens? So imagine that I want to now restrict the access.
Yes, so very good point. Something that is important about these tokens is that you don't want to make them without expiry. Like, they cannot be infinite, because inherently they can live forever, and they will be forever valid if they have no expiry. So what companies usually do is they have very short expiry for these tokens, maybe 24 hours. So even if, for example, a person works at a company and he has access to the internal network, in 24 hours he can lose that access, and no one needs to worry about it. So, 24 hours is a good deadline. Some other places have it after 8 hours, so that tokens can expire fast. But also there is a concept in the Open ID protocol. There is also like a list of tokens or public keys that shouldn't be used to verify these tokens. And so there are these lists that are also publicly available, but the concept there is a little bit more complicated. But it exists as a solution.